Okay, well, welcome everybody to this question answer session. This is a new way of doing things. We recorded a talk, and Viv's got a paper to talk to as well, which has part of the stuff that's in the talk. So the idea was to listen to those and read the paper, and then come up with questions, and then Viv and give an opportunity for people to put views on any of those questions. So we'll then have three objects to this potentially extremely important piece of work. I'm very curious to see where experiment goes on this, Viv. It looks like a lot of fun coming up in the future on it. So without further ado, I think I'll throw the meeting open to any questions that people have over any aspects of the theory to put to Viv. Over to you guys.
Could Vivian give us a summary of his point of view on theory?
Okay, the briefest summary is, as we know, Einstein's general theory of relativity is that mass distorts space-time, producing gravity. Fine. What is space-time? I mean, it's a bit more than just a clock, a box with a clock in it, a bit of space and a bit of time. No. Space-time, so Einstein never actually defined what space-time is, but space-time curvature, as he showed, it predicted quite a few things accurately, so there was a lot to his theory. Now, my contention, was the two things. Firstly, the paper that I had published just says, hang on a minute, you guys, when you're talking about black holes, you've missed, Einstein never believed in them, and you go through his paper, you find out he introduces approximations. The approximation he introduced, well, first of all, by using tensors, it's an approximation, and he admitted it when he wrote them. That approximation is pretty good until r equals the radius of the distance from the center of mass is about 3 times the Schwarzschild radius. I reckon that's a pretty good approximation. But the other approximations he introduced were the equivalent of 1 over 1 plus alpha over r equals 1 minus alpha over r. Now, when alpha over r for Mercury, for example, is less than 10 to the minus 7, hey, that's a pretty good approximation. Unfortunately, those who solved his paper didn't really understand it, and I'm not surprised if you go through it. It is difficult to follow, but not impossible. So when you do follow it, you find out that the solution he came up with was 1 over 1 plus alpha over r. But everybody, and perhaps following Schwarzschild, used the 1 minus alpha over r approximation. Then they extended that from the area which it was really good at, 10 to the minus 5, 10 to the minus 8, etc., and even around Earth, 10 to the minus 14 or 15, somewhere around there. They extended that to r equals alpha. Now that is outside the range of applicability of the approximations he says he used. And it's not as if you have to read through it to find out what to find those approximations. You have to go through it carefully, but it's not impossible. So that's the first bit, that all of general relativity using the 1 minus alpha over r term is wrong. It gets good answers though. It gets the same answers for everything except Mercury's precessing orbit. Now, for an orbit for a Mercury or a star S2 to precess, gravity must be weaker than inverse square. I mean, Einstein pointed this out, not Einstein, Newton pointed this out in 1687. And the physical reason for this is that if gravity is weaker than inverse square, then Mercury or the planets orbit a little further away from the massive body, the sun, and they're attracted by a weaker force. Therefore, they will take a little longer to return to their, let's say, their aphelion or perihelion point, and that means that each time it will precess in their orbital direction. If gravity was stronger than inverse square, then it would travel a little closer to the star and be attracted by a stronger force, so it would arise back at its starting point a little earlier in each orbit. It doesn't. They arrive a little later, and that is the experimental proof that when Einstein said he did not believe in black holes, they were not physically possible. Now, what I've done in that presentation I've just given is turn around and say, okay, what exactly is space-time? That paper published in the Institute of Physics says that redshift...
Viv, can I interrupt a sec? There's one bit you've missed out, which is to say what you're using. You're using the exponential of alpha over r.
Oh, yeah. Yeah,
So
well,
both of those.
if I could just, at this stage, I'm just going over the difference between mine and Einstein's. Now, Einstein never believed in black holes. The calculations, the difference that you get between 1 minus alpha over r and 1 over 1 plus alpha over r is exceedingly small. But it doesn't, the only difference it makes is the minus sign should actually predict that Mercury's orbit and star of S2, their orbit should regress against their direction of motion. They don't. Now we come to what is space-time. So the distortion of space-time is redshift. And space is the absence of anything, which makes it rather difficult to compress or stretch or bend. But I've used the finding that in 1911, Einstein pointed out that he thought that the curvature, that the mass changed the refractive index of space, but he never expanded it on it, and a few other people have looked at it. When I expanded on it, to find a reason, it was the same thing, a change in refractive index deflects light, it's a standard thing. I then when I went through the calculations, I found out that the differential of the electric permittivity of space gave G equals gravity Gm over r squared e to the alpha over r. Now, r squared or e to the alpha over r is never a negative number, so it's always positive, which means that gravity is weaker than inverse square. The second thing is in that paper that I published in the Institute of Physics journal, I did the integration of Einstein's work, just integrating gravity, and got exactly the same expression. So that's why I'm reasonably confident that my approach is accurate, because in one approach, I integrate the redshift and to get an e to the minus alpha over r on the bottom line. And the other approach, I differentiate the electric permittivity of space to get the same equation. So I've got it from two separate things, and my whole argument is that what is called space-time distortion is just changes in the electric permittivity of space that are induced into the space using Feynman's work, where the high frequency oscillation required by Feynman is just the high frequency of the rotating photons that are the nucleons. Their frequency is a few times 10 to the 23, and they just accumulate until they're saturated. So that's the general summary of everything. And the deflections caused by that produce the gravity that we know. Now, a single photon passing close to the huge mass of the sun, a single photon passing close to it, what's it distorted by a very, very small amount. But when a particle, which is a rotating photon, is subject to that distortion all the time, that is what attracts massive particles to other particles. That's basically the summary. It matches everything I know about gravity, with one exception is that Newton only actually pointed out that gravity was proportional to 1 over r, the mass, the product of their masses divided by the square of the distance between the centers. He didn't give the gravitational constant. That was added by others. Einstein used the term a little k for what we use as g. Okay, over to you.
Well, Viv, I think it's a very interesting conjecture that you're coming up with, that the force that the force law, especially at short distances and for high masses, differs from the Einsteinian one, and that the Einsteinian one is a first approximation to the Newtonian one is a 0th order approximation. The Einstein one is a first order approximation to the one that you have found. I think that's very telling. It means that in a large number of situations, that all three are indistinguishable. And so you have 4 possibilities. You have Newtonian, pure Newtonian, g m1 m2 over r squared. You have the modification by a 1 plus alpha over r, divided by 1 plus alpha over r, divided by e to the alpha over r, the Robinson one. And you also have the 1 minus alpha over r, the Schwarzschild one. So there are 4 possibilities: Schwarzschild, Einstein, Newton, and Robinson. So, and then you investigate those different possibilities to see where they differ and what the effects of those differences would be. So,
yes, well, yeah. I would just like to say the one thing that I'm sure you're all aware that, well, 1 over e to the alpha over r, for example, when alpha is much, much, much smaller than r, then that becomes 1, and so you have Newton's, accepted Newton's equation, gm over r squared. When alpha is much, much larger than r, then e to the alpha over r becomes 1 plus alpha over r. And then you get the Einstein, well, I should point out at this stage, Einstein did not solve for the gravity. You know, his field equations don't give you an equation, G equals gm over r squared 1 plus alpha over r. All he solved was for the difference between Newton's law, which is gm over r squared, and his law, which turns out to be gm over r squared times 1 plus alpha over r. So that's all he solved for. It's very straightforward then to say that Einstein's gravity is actually gm over r squared times 1 plus alpha over r. But that answer is still, the gravity is still weaker than inverse square, because 1 plus alpha over r is either 0 or a positive number. And the only reason I think that everybody else has used the 1 minus alpha over r, which then becomes, in the Schwarzschild solution, which then becomes g over r squared 1 minus alpha over r, is because Schwarzschild actually introduced an approximation and then used that negative sign, which was fine. It didn't make any difference whether 1 plus alpha over r in the top line or 1 minus alpha over r in the bottom line. It didn't make any difference when r is much, much smaller than alpha. It's only the extension as r approaches alpha that you run into problems. And they say the single exception to that is that if people paid attention to their mass, they'd find that because they use the minus sign, then Mercury's orbit should regress against the direction it travels. It doesn't. That should have been a wake-up call to someone somewhere along the line, but it wasn't.
To me, an obvious wake-up call is there's no physical force that could have an infinite magnitude, so that should have been a red flag that it was an error in the math also, in my opinion.
I don't know who said it, but nature abhors a singularity. I don't think it was Einstein, but no. Again, that should have been a wake-up call also. You can't get a singularity.
I think another thing that you've emphasized, and which I think is quite likely correct, is that the way that Einstein wasn't didn't present this work, and also the calculations that have been done have not looked at the complexity or lack of complexity, in fact, in the force of gravity. They've looked at the tensor part of the whole thing, looking at the stress tensor and the mass energy and the energy momentum tensor part of things, and that complexity has. So working with that complexity and with any of the four approximations, people have thought that the theory really is looking at the tensor part of this, where in fact, of course, one uses tensor algebra in lots of other cases. If one's looking at the inertia tensor instead of just simply the mass, of course, that's important when you have a scale involved. So, but the way the thing scales is for the large scale structure of solutions is far more important than whether you're using tensors or scalars or any or Clifford algebras or whatever. And I think that's been overlooked because of the complexity of the mathematics of the way that the tensor algebra has been looked at as being bend in space-time.
I'm sorry, John. Yeah. Okay, I'd like to explain something that people don't seem to be aware of is the actual paper in which he published foundations, the gravity theory was foundations of the general theory of relativity. And as you read through it, what he starts out by saying, look, I've taken care of special relativity, which is two objects at a uniform velocity away from each other. And then he wanted to work out what would be the equivalent for particles accelerating with respect to each other. But it wasn't just this particle accelerating this way and this particle accelerating that way. It was a curved acceleration as well. Now, in order to get a curvature, you do need tensors. I mean, you need three vectors and time to get it, which is turns it to tensors. He then went through his paper, and if you read it, you can follow it. He went through his paper trying to work that out, and then my own personal opinion is that he got a little bit lost. That situation really is very, very complex. And then realize that, well, hang on, I can get gravity out of this. So what he started out, the foundations of general theory of relativity, just finished up. The best way he could finish it up was then to derive his gravity field equations, which of course are still curved. But to give you an example, if you have a look at when Newton derived his inverse square, it was a few sketches, a little bit of geometry. It was all done on a page or two. That's when he'd done a lot of build-up work to that over a few pages. But the actual derivation of the inverse square law bit was just a page. And you have a look at my derivation of G equals GMM over R squared e to the alpha over R. It was just a few pages as well, and quite a lot of commentary. And then finally you get to Einstein's foundations paper. When he derived it, he used almost 60 pages and comes up with the difference between Newton's theory and his theory. He doesn't come up with a theory, so you start to realize out of that, well, was all of that necessary? My answer is no, but I think he got there because he was starting out to solve the general situation of an observer here and something else was traveling in curved path. That's what he started out to solve, and just decided that the easiest to let's finish it off with gravity, which is probably the only useful aspect of it. And I think that may
Go ahead. Don't we usually summarize Einstein's theory by saying that he looked for a tensor expression in terms of the curvature in the differential geometry that would have zero divergence, so that he could match it with an energy matter tensor. And it took him a long time to find it, and there's some complexity there. That's where the complexity lies, in finding that curvature tensor that has the right property, and then setting that proportionality. So there's this large idea in general relativity that is at a different order than looking for a single equation like 1 over r squared.
Yes, I don't believe my reading of his papers. I didn't come across a single equation or even a set of equations where he was defining those. He
Well, there's
set out,
Einstein's field equation. That's what I'm referring to.
yeah.
That on one side is a curvature expression, and on the other side is a expression in terms of measurable physics.
Okay.
That's absolutely correct. But what he's doing in terms of, but the point is that one can express this in a different way. One can go via the curvature. One can assign the change in to a change in spacetime, which is indeed correct. Then work out what that change is in terms of Riemannian tensor algebra. But then coming back to the change that one gets from the Newtonian case, and it's a small change in many cases, is what Einstein calculated. So he's looking at that small change. He didn't go via the possibility of just making a small change to the force law.
Right, he didn't. He was looking for this big picture,
yeah,
and
very,
then
very
he would
brilliantly
find out
too.
what changes happened as a result of the big picture.
Yes, he was. And very brilliant it was as well. This is an alternative way of looking at the same thing, but with the assumptions to the way that I suppose what's happening here is that the underlying assumption as to how space and time is affected is different in the 4 different cases. So it comes down to then saying, okay, you have bent space-time, and you've managed to, but what the hell is space, and what the hell is space-time? What is space-time? What is the physical underlying nature of that space-time? And if you don't know that and simply put it onto some tensor mathematics, fine, it's a beautiful theory. It's as good as any we've got. But is it correct? Is it physical? And then coming to the physicality of things is what Viv's looking at here. And a different kind of physicality gives the same results, but also tells you what's changing and why it's changing. And then the question is, well, is that correct? And we don't know. We need to do more experiment to find out. But I think that's a very beautiful endeavor to try and look at those differences.
What Einstein, although yes, I understand what you're saying about he did come, but his field equations were not a calculation of gravity. They were a calculation of the gravity difference between his theory and Newton's theory. Now, there's a big difference between the two. If he did succeed in doing the 3-dimensional curvature of space, then he would then have found the equation, including Newton's gravity, because Newton's gravity is very strong. It's a very powerful force. To get total curvature of space, he would have had to add Newton's gravity to his theory. The fact that he has got just the difference, these field equations and tensor on one side and curvature on the other, etc. The fact that you've got that, but only for the difference between his theory and Newton's theory, to me suggests he didn't actually get what would be the full equation. Now, I would like to add one other thing, that there seems to be a lot of concern about photons having mass. Einstein said photons had mass in 1905. Or they weren't known as photons then. He just called them little packets of electromagnetic energy that traveled very fast and conveyed inertia between emitter and absorber, have mass. I don't know why people want to prove Einstein wrong. The first one, of course, was their exact solution predicts gravity is stronger than the inverse square black holes. Einstein just said he didn't believe in them. I don't blame him for not solving not showing the solution that he got, and it's not his fault that others can't follow his work. And then you have Einstein says photons have mass, and everybody says, oh, no, they're massless. And one of the reasons they use for that is his special relativity corrections of m mass of velocity equals m naught, rest mass divided by 1 minus b squared over c squared. Well, clearly, if they have a rest mass, then traveling at c, their mass would be infinite. But they don't have a rest mass for the simple reason they can only exist traveling at the speed of light, which is governed by the electric permittivity and magnetic permeability of space through which they're traveling. But
let me explain why people have trouble with that, Viv. And this was one of Lee's objections when you said at the beginning photons have mass. Many people, what we're talking about is we're talking about what people mean by mass. So if you're looking at the energy momentum, if you're looking at the total system, sort of as a high energy physicist, as a particle physicist, in order to conserve momentum, one needs the photon to have momentum. It needs to transfer momentum. It needs to switch inertia, as you say, from one thing to another. So as a high energy physicist, with my high energy physicist hat on, then these things transfer momentum. They have a rest mass, which is 0. And what has happened is that people have taken the rest mass being 0 to mean that the photon is massless. This is a given thing that nearly everybody believes. Photons are massless. Photons are not massless. Photons are rest massless. And one has to really understand properly what one means by mass. Photons can be weighed. If you put them in a box, in a light-tight box, then in a gravitational potential, you can weigh them. Their energy is their mass is E over c squared. And you can prove that. It's quite a simple thing to prove. Martin did with his paper, Light is Heavy. So now that might be that might be obvious to you or me or Einstein that that's the case. But for most physicists, it is a canon of being a physicist that the mass of photons is 0. Simple. Anybody who says anything else is a crank and should not be looked at further. So that's what you're up against when you say that kind of thing. There's a whole bunch of people who are just going to say, no, obviously that's not what he's talking about, click off. And you may not like that, but that's the way it is. One's talking about different kinds of mass. So what Einstein was saying, or was talking about, is that photons have a gravitational mass. Now that's a different thing to an inertial mass or an invariant mass or a rest mass. These are all different things. Well, some of them are close to one another. You might say the invariant mass is close to the rest mass, or it is the rest mass. One can calculate the invariant mass by having a look at m squared is equal to e squared c fourth plus p squared c squared, where the momentum of the photon, of course, is given by E over c, as it is measured to be in a high energy physics experiment. But not everybody's a high energy physicist. So when you say photons are massless, most people just go click, no, look at Wikipedia, no, they're not there. Everybody knows the massless guy obviously hasn't a clue. And nothing could be further from the truth, but that's what's happened in these.
I agree that your equation E squared equals P squared C squared plus M naught squared C to the fourth. That only, if you understand that, is Einstein's special relativity. It only applies for particles like electrons, protons, neutrons, neutrinos, etc. It doesn't apply for photons. But if you put the m naught equals 0, which is rest mass, then you get E squared equals P squared C squared, which is no problem. Now, what they turn around and say that photons transfer their energy through momentum, not mass. But however, any dictionary definition of momentum is as mass times velocity. So in that way, photons do have mass. But as you say, it's gravitational mass, and by convention, I agree with you. Particle physicists, when they define the mass of something, they define it as its rest mass. Now, quite a few people use gravitational mass. Other people say no, because of this E squared equals P squared C squared, and drop off the m naught squared C to the fourth. Therefore, with no m naught, there's no mass. They just forget that p is mass times velocity. And they forget that bit of mass, and that's where the problem comes.
Just speaking as a former particle physicist, I would probably agree with John that I don't think of mass at all other than rest mass. It's an interesting question, of course, where particles like neutrinos, whether they have a rest mass or not, and it's also an interesting question of whether photons have a rest mass, and those questions can be answered experimentally. You can put experimental bounds on those. And I think a particle physicist would never equate mass with momentum.
Yes, I agree, but I'm just saying that the photons are different from particles. You can't treat, because in reality, but in John and my model, all particles are photons that make 2 revolutions per wavelength. And in comparison to the standard model, for example, standard model has about 61 variables that they can fiddle with and can't get answers. We have four fixed things. We got the linearly polarized photons and circularly polarized photons, and then you have rotating plane polarized photons and rotating circularly polarized photons. That's all you've got, and with that we can basically have explained an enormous number of things that standard models can't explain. And this is what I am using photons with mass, and they still have, even when they're turning around at the speed of light in a very small circle, they still have mass, and that's what gives particles their mass. But I agree there is this interpretation by particle physicists that to talk about rest mass, but in the case of photons, they never exist at rest. They can only exist at traveling at the speed of light. And E squared, P squared, E squared equals P squared, C squared is...
That's not quite the case, Viv. I mean, particle physicists have quite a subtle set of things that they talk about with photon exchange. So when you're talking about real photons, one talks about them in particle physics as being on mass shell, if they have 0 mass. But when one talks about quantum electrodynamics, one goes to photon exchange. One then talks about the form momentum transfer, usually the form momentum transfer squared. And a virtual photon can carry mass, but it can carry positive mass or negative mass. So in QED, the transfer for attractive, if you imagine just thinking about the physics of throwing a medicine ball between 2 people, if you throw a medicine ball from person to person, it repels both of them. Both of them are pushed backwards by the force of the medicine ball hitting them, then rebounding and coming back. So the way you treat that in QED is you treat the form momentum transfer squared as the mass of the exchange photon being negative. Now, that doesn't mean that there's a negative energy involved there. It means that the form momentum transfer squared is attractive. We're talking about 2 oppositely charged particles. So there's a whole hierarchy. People are not being very simplistic in particle physics. They're actually being even more subtle in terms of what the properties they're putting onto photons and these things. So it's not that it's not merely the fact the photon is never at rest. It's that a photon, under certain circumstances, under certain boundary conditions, can exchange negative effectively. One describes it, it's a sign change, but it is described in those circles as being an exchange of negative mass rather than positive mass, or energy, form momentum transfer squared properly. So one's not talking about mass at all. One's not thinking in terms of mass. One's thinking in terms of form momentum. One's thinking in terms of something which is more complicated and more subtle.
Okay, but there is one thing that whether refraction of photons being caused by the changes of electric permittivity doesn't matter whether photons have mass or not. whether you treat photons as massless or whether you treat them as mass of h nu over c squared, it doesn't make a scrap of difference when you're talking about photons passing through a varying or passing through an electric permittivity. They're slowed down, they're deflected, irrespective of whether you're talking about them having mass or not. Now that's for photons. It makes a difference, of course, for or maybe one could say, well, if a particle is a rotating photon, then it will get the same effect, whether it has mass or not.
Yeah, that's true. That's true. I mean, momentum is only transferred at the interaction, at the ends of the interaction.
So I think that there is this enormous difference in how different sections of science treat the same thing. At the one end, we've got the huge universe, and at the other end, you've got subatomic particles. Now, as far as I'm concerned, they can all be treated as the same. And I understand what you're saying about negative mass, but in my work, which I haven't progressed very far, and I don't intend to because I can leave this to others, but a circularly polarized photon has a spin of h bar. And that spin can plus h bar or it can be minus h bar. As far as I can work out, if two positive photons exchange, two positive particles exchange a photon, then a plus h bar leaves here and goes across to the other one, which then adds to the mass and they repel each other. Whereas if a negative h bar one goes from a negative to a positive, then when it's absorbed, it lowers the mass of the photons and brings the two together. That's as far as I've got in this study. Well, it's a bit more to it, but that's it. And that would be how I explain the difference between positive mass electrons repulsion and negative mass electrons attraction. But that's, like I said, that's as far as I got. And my interest was having got gravity, I think and as I said, whether they have mass or not, the deflection of a photon by a change of electric permittivity does not depend upon the mass of a photon. It depends only on the properties of the photon. And hey, look at Feynman's work.
I suppose the question I would have there is then why I suppose talk about mass at all. When I was reading the paper, I was sort of struck by you're referring to mass, but it didn't seem necessary. You could have just referred to the energy of the photon, as far as I could tell.
Yes, and that principle of changes in the refractive index basically equals changes in the electric permittivity of space. It is that which deflects photons, changes their wavelength, and it does that. And from what I presented in that earlier paper, it does that in exactly the same way as gravity. And it doesn't matter whether that will occur whether photons have mass or are massless.
I guess why then make the statement in the paper that photons have mass if it's immaterial?
No, I didn't because I was, I suppose after a while one gets wrapped up in my own work. And the other thing, of course, is Einstein's E equals mc squared. It's fairly derivative. If you've got energy, you've got mass. And so if the photons have energy, QED, they have mass. And no matter how you approach the mathematics, even if you put the rest mass of the photon is 0 and come back with this E squared equals P squared C squared, P is mass times velocity. So you still have mass.
I guess you could equivalently say that sort of mass is an apparent phenomenon, not an actual one. That is to say that there is no such thing as mass, there is only energy, if you wanted to.
Well, you can use that, of course, yes. However, the general public is well and truly aware of mass.
I guess I have a question. Your take on quantizing gravity, and the common law is that gravitons are massless. So vis-a-vis this discussion, how would you characterize the gravitons, if at all?
Gravitons are like string theory. It's a very good mathematical approach, but my approach to physics is work out the physics first and then then carry out the calculation. And if the calculation doesn't match observation, it's a big no-no. And I had somebody came up to me and said, I actually worked out a theory that gravity depends upon the molecular structure of some molecular property. And I'm saying, yeah, okay, well, there are actually no molecules in the sun. And its gravity is very strong. So the guy said, yeah, okay, I'll drop that one.
Well, the experimental context I might put this in would be the observation of gravity waves. And that you can either say that you can dispute that, but if you think of gravity waves like light waves traveling at the same speed, you have some similarities between photons and gravitons, which is experimental as opposed to string-like nonsense. Not nonsense, but well.
Yeah.
So
okay,
then you
well,
would expect your gravitons to have mass, but not rest mass, similar to photons.
oh yeah. Oh, sorry. Okay. No, I'd just like to answer your question first about gravity waves. Gravity waves would then, under this model, would then just be an increase in the electric permittivity generated by this huge, rapidly rotating things. All that does is it sends waves of increasing electric permittivity back to normal permittivity. That's all gravity waves are. Now, one
I
of the
think
things. Yes, John?
may I jump in as well on these gravity waves? Because I think this is such a beautiful thing. I think that experiment and those ringing sounds were just an absolutely amazing piece of progress. But I think the thing that made the most impression on me is and this was a question that we've been asking ourselves for some time before that, whether the speed of gravity was the same as the speed of light. What Lou said is absolutely right. I mean, the thing has to be massless or near massless because it's such long range. So it certainly has to be that and have the same sort of mass that photons have. In other words, rest massless or very nearly rest massless. But I think the thing that really got me, and I think this is another feather in Viv's cap really, is that we're talking about something which is very, very light-like. The speed of gravity is the same as the speed of light, experimentally from those measurements. This means we're talking about the same sort of thing. And I prefer a wave in epsilon to being something that's a rate of change of the interaction with the number of gravitons, with graviton exchange. I think it's a nicer physical concept that what you're doing is you're putting a wave into space-time, and that's transmitting through space at light speed because it is of light. We're talking about epsilon zero here, which is that thing which defines at least one property of light. That's the speed of light, this infinite speed.
Yeah, I agree totally with you, John. Electric permittivity determines all of the properties of everything. It determines photons. If you haven't read Feynman's work, oscillating electric fields change the permittivity of space, but that change only has an effect if the oscillations are at a much higher frequency than the photons that are being deflected. So you can't just turn around and get a few tens of kilohertz or megahertz of frequency and then say, oh, we'll get gravity out of this. If you want to get artificial gravity, then your frequency has to be 10 to the 40, something like that, hertz, which is roughly what we have in the sun and around here. but it's still an electron, it is still a property of the electric permittivity and mass. And so the reason I called it quantum origins of gravity is because it is the property of an individual nucleon. It's not that.
Viv, let me jump in and say why people are pushing against that as well. When people talk about quantum gravity, they're normally talking about quantizing the exchange particle. They're talking about gravitons. That's what people see when they hear that. When you talk about quantum gravity, you're talking about the way that the quantum level affects or is part of the mechanism of what gravity is, which is more fundamental and perhaps more what quantum gravity should be, but it isn't what people hear when you say quantum gravity.
It's the sun's gravity is quantized in bits of 10 to the minus 57. That's quantized gravity for you. But I agree with you that they've come to think that who was it? I'm not sure it was Dirac or was it somebody else who introduced the idea of quantized gravity through particle exchange. I'm not sure, I don't remember. I thought I read somewhere that it was first introduced by a Russian scientist and then Dirac.
Yukawa is one of the famous names associated with exchange, but quantum electrodynamics, that was Feynman.
But one of the other things I might add that a lot of if you're talking about something that exists which doesn't have mass, or even something that does exist, it's got to have something that it's composed of. And I would use the situation, an electron is an elementary particle. Is it composed of electronium, for example? It's something, and it needs particularly when it comes to quarks or quarks, it needs something. It exists. You can't just say it's something. You got to give it. Is it quarkonium up or quarkonium down and that sort of thing? And how do they interchange to give electronium and neutrinium or whatever it is? This is what physics is about. It's what is this stuff made of? Not mathematics of this is how it interacts. Yeah, that's fine. However, unless it's got some physical reason behind it, my opinion is it tends to be, let's say, questionable. And the mathematics, as I say, the whole cosmology and the Big Bang theory depends. Well, no, just stick with black hole. The whole black holes, wormholes to different parts, all because people went through the math and missed a minus sign. And that has caused an enormous problem in cosmology. Things are trying to explain things that don't exist and that. And that's why, in my opinion, you're vastly better off giving a physical description of what's going on and then using maths to back that up. Mind you, if you've got this wonderful physical description, but the maths is hopeless, well, forget the physical description, go on to another description until the maths meet. I think it was Roger Bacon about the 13th century in England said that maths is absolutely essential for science. And I agree with that. You cannot have a serious scientific presentation without the maths backing up the science. But I think we've gone a little bit too far. And I think a lot of people have been trying to imitate Einstein by using mathematics only. And Einstein, I've quoted this before, Einstein's theory was, if I can't visualize it, I can't calculate it. And I agree with that. And I think that's one of the reasons why I think I've been able to go through and work out the thinking that he was using when he came up with those ideas. But I think too many other people just say, oh, okay, well, let's start out with this. I actually read a paper once I won't mention, I forget the guy's name, but it basically says that it goes to the enormously complex maths, and then turned around and said, and that is why gravity weaker than gravity stronger than the inverse square makes makes Mercury's orbit precess. And I'm not going to go through all of that complexities. All you've got to do is, and I'm sure this has occurred, reviewers don't like to acknowledge they don't understand maths. So I think if they look at something and say, oh, that's so complicated, I'm going to pass it because I don't want to admit that I don't understand it. I'm not sure that that's always true, but I think that happens with some papers.
I guess
I
I have
have-
I'm sorry.
Oh, sorry. I had another question, I guess, relative to the Schwarzschild solution. A lot of noise is made about the fact that the metric is singular at that point, and it's not a real singularity, and that it's a choice of coordinates. With your approach, you don't seem to have a singularity when r is equal to alpha. You want to comment on that? Is there like a Schwarzschild radius, or is there a difference in coordinate systems?
The Schwarzschild radius very much is a physical phenomenon. It's 2gm over c squared, and all of those are positive. So 2gm over c, so it is a physical concept. It's much easier to carry out the calculations with alpha over r than it is 2gm over c squared. It's just a bit more complex, but getting a singularity is not, with the Schwarzschild metric, very much is a mathematical mistake. Getting a zero is quite possible. I mean, you get far enough away from any mass, the gravitational attraction is essentially zero. The other one is that e to the alpha over r on the bottom line, when r is so small compared to alpha, then e to the alpha over r becomes a very, very large number, which means that the gravitational field at the center of a massive object is always zero. Now, we know that with the sun from Newton's shell theorem. The pressure and the temperature in the center of the sun is huge, but there is actually no gravitational field at the center of the sun. However, I don't want to be the guy going to dive into the center of the sun and try and measure that. And so having zero gravity is quite fine. One vastly far away, way away, and the other one is at the center of a massive object. There's a speciality about r equals alpha over 2, and that is when the gravity is at its strongest. When r gets smaller than alpha over 2, then gravity starts to get weaker because e to the alpha over r then becomes stronger, a larger number than r squared.
When r is equal to half alpha, that's where the accretion disk occurs.
R equals half alpha is where the gravity is at its strongest.
If that's true for yours, for your metric, talking about metrics as Jerry's doing there, but for the metric that we're talking about with Schwarzschild, that at alpha equals r, it goes to infinity. For Einstein, it doesn't. There's not a singularity there. If one looks at 1 over or 1 plus alpha over r, there isn't a singularity at that point, because alpha, it's just 2. It's just so you're nowhere near any kind of infinity. So
Yes.
So it depends which effective metric, if you like, although I wouldn't call that I wouldn't use the word. It's again, people use metric in different ways in different fields. I wouldn't use that as a metric. I'd use plus, minus, minus, minus as a metric, but people do. But so if in the Einstein metric we're 2, in your metric we're we're a maximum at r equals to half.
Einstein's metric does finish up going to infinity when r equals 0.
Oh yes, okay, that's true, but the integral still goes to 0 because you're still talking about
the same
Showing
as
it.
Newton's gravity goes to infinity when R equals 0.
Yeah. So in fact, gravity still goes to zero because of the shell law. But actually, I had another question, another set of questions, which I wanted to put to you and which I haven't got the answers to. So, and that is, if we're looking at these objects which have been seen, which are these donut objects with a black bit in the middle of them at the center of galaxies, at the center of our galaxies and 877, I don't really see. You've looked at the thing as a sort of a two-dimensional thing, and if I think about, okay, so if I switch to the Schwarzschild idea that there is a black hole, I don't actually get why there's a black hole shadow. People say there's a black hole shadow there, because I would imagine, because the light isn't coming from the black hole, the light's coming from a shell of stuff around the black hole, which is emitting stuff. So I don't get why there's a hole in the middle of it, unless we have an accretion disk. We have something which is spinning, has some angular momentum, and therefore the stuff is concentrated in a ring-like structure, in which case I do get what's going on there if we have a black hole. Likewise, if we go to the Robinson metric, if we go to then, once again, I don't see, because as you say, even though the gravity at the center of the sun is zero, the density and pressure are very high there because of all the stuff pushing down on it. If I imagine having the gravitational thing at a half the Schwarzschild radius being a maximum, so stuff tends to go to that, I would think that one would then get a mass ring only if one had enough angular momentum to make sure the stuff was being brought into what would now be a toroidally shaped object. That's the way I'm imagining what would happen with your system. Would you agree with that? I mean, how do you visualize what's happening with the Robinson metric for a very large 300, 3,000, 3 million solar mass object, like the thing at the center of
Again,
galaxies?
what is happening? The thing about another reason for using the alpha term of 2gm over c squared is that normalizes everything for any mass. And what happens at alpha over 2r is independent of the mass. Now you have this huge mass at the center of M87 was a few billion solar masses. If you just to a first approximation, you can work out the velocity of incoming particles that are attracted by it by using the reverse of Newton's escape velocity. And that then gives you, with an alpha over r, when you're at a certain, whatever the alpha over r term is, whether it's 1, 2, 0.5, 3, or whatever that is, the infalling material will always be the same. Now, it turns out that for alpha over r, in Newtonian gravity, everything is traveling at about, around about 0.7 c attracted by the gravity. Now, a huge mass, of course, 0.7, the speed of 0.7 c is reached much, much further away than for the smaller mass in Sagittarius A, which is only 20 million. But at that alpha over r distance, the speed will be about 0.7 c.
I think this is a great opportunity for proposing something. That is namely, it seems to me that with the Robinson metric, as opposed to the Einstein as opposed to the Schwarzschild metric especially, one is looking at an object which concentrates stuff at a much, much bigger radius. The radius
the radius is half alpha, and the black hole radius, where they say is going in, is alpha. What is interesting is that they turn around, because the temperature that they indicate there is about 10 to the 10th degrees K. The velocity would give an electron, the energy equal 10 to the 10th K would give an electron a speed of about 0.7 c. Whereas if it was a Schwarzschild one, where it was attracted by an infinitely strong field at r equals alpha, it would get to a higher temperature than that. Let's get to a higher velocity. These things are colliding with each other. If all they do is disappear down a big hole, they won't emit radiation, unless of course.
a thought from that for the space people, for the NASA people. Do we if we're talking about light from a black hole, we're talking about stuff from an accretion disk outside the black hole. I guess the numbers are quite similar in terms of looking at the reverse escape velocity. Do we have does that correspond to the size that's been observed of the donuts that have been observed in 877 and so forth? I mean, that would seem to me to be what sort of radius are we talking about here? We're talking about a half
Depends.
Alpha.
Yeah, once you get beyond whatever the distance is, then you're back to Newtonian mechanics, and it doesn't matter what the strength is, where it starts out. You're back to Newtonian mechanics by the time it's measured. So you're relying on you can't measure the mass of the object at the center. You're relying on a calculation to calculate it. Now, the calculation that you get with the Schwarzschild radius, I think for Sagittarius A is about 5 billion solar masses, whereas the calculation that you would get with mine may be 10 billion solar masses, but it's a calculator. You have no way of measuring that.
Wait a minute. Can't you measure it, one, from what the gravitational effect of that object on local things, the orbits of local things, wouldn't that affect that? And the velocities going away and coming back at you, for example, there's a Doppler shift. That would be one measurement. And then the other measurement would be from the size of the object, would it not? These are independent measurements, both of which should give you an estimate of what sort of mass we're talking about.
The Schwarzschild, the physical radius becomes larger than the Schwarzschild radius, around about a few million solar masses. So the 20 million solar masses at the center of Sagittarius A, yes, they could use that to, they use the precession of the star S2 around that mass to calculate the mass of the massive object. But when it comes to the center of M87, all they can, they can't measure the individual stars. It's just far too difficult. All they can do is get their collaboration. Everybody gets in and crunched by computers, and out they come with those curves. And they are a real phenomenon.
Well, I don't get that, actually. For something as far away as Sagittarius, how are you getting the resolution to see that there's a hole in the middle?
The measurement you get out of that depends entirely upon the metric you use.
Yeah, but how do we see the donut? Surely.
You're seeing the donut because at r equals alpha over 2, you've got all of these things rushing in. They get to maximum speed at alpha over 2. They would, of course, like anything else, like rolling a marble down a shape like this. It'll roll down, it'll go through. If it doesn't get stuck or doesn't fall over a loop at this end, it'll roll back, and they'll keep rolling back, and they'll have maximum because
no, I understand why there's a donut. What I'm talking about is how is the angle of the donut being resolved at that distance? We're talking about something which is far further away than Sagittarius A. I'm just curious. I mean,
I think the statement was.
Sorry, it's not a question to you, though. It's just I was just gobsmacked that people could resolve it at that distance.
Yeah, the statement was that Sagittarius A is a very small, massive object, very close. And M87 was a very large object, at a very great distance. So the difficulty is the same.
Okay, I'm with it. I finally got it. Sorry, it was a stupid question.
Well, I have my own stupid question, and just a clarification. Your solution says there's no black hole. So I think what you're saying, and just help me if I'm wrong, that except at r equals 0, there's no point at which light cannot escape.
No, yes, there is no point at which light cannot escape. Yes, I mean it has some other implications that my metric has some other implications as well. Once you get a very, very massive object, under this model, a neutron, well, first of all, gravity compresses photons into electrons, and you get neutrons, and you get a massive neutron star. But what happens is as the star gets more and more massive, the center of gravity is now outside the diameter of the neutron star. And what that means is that gravity is pulling on the outside of the star. And so as the mass gets bigger and bigger, the gravity pull will reach a stage where the gravity in the center of the neutron star is not strong enough. And because it's pulling out, the pressure is also diminishing. The gravity will get to the stage where the center of the neutron star has very low pressure. And when that occurs, the neutrons in the center will then break down to go back to protons and electrons. And then they will build up to huge, huge pressure. Ultimately, the weakest point of a neutron star is its axis about which it rotates, because all of the neutrons, everything traveling, orients itself or travels in a direction where its rotating photon is always, the rotation of the photon is always perpendicular to its direction of travel. That's why they can measure the charge distributions of protons and neutrons and nuclei so accurately. So the center, the rotation axis is the weakest point. You eventually get to a stage where the pressure buildup is so strong on the inside that it will break through at that point. And as far as I'm concerned, that's the origins of your quasars, that they get all of this mass that comes in, swallows all the entropy with, and gravity. I don't know why people worry about gravity, about entropy. I mean, gravity reverses entropy anyway. Even in the real world around us, it does. Everything goes into this, it's converted to photons and neutrons. The neutrons then eventually in the middle of it become hydrogen again, and of course the temperature will be such that some of that hydrogen will fuse to some helium and detect it up to magnesium, and then the whole thing explodes. And what you then have this huge mass, and the redshift that you're seeing from galaxies, from quasars, is Holton up pointed out that the huge redshift from a quasar, but it was actually associated with a closer galaxy. And then all that happens, you got this huge mass, and all the gas is trying to escape from the center, and I'll let you to work out, but how long it will be, but it would take an enormously long time to empty itself of the high pressure hydrogen. And that's basically the way, as far as I'm concerned, that's basically the way that an infinite steady state universe just keeps recycling everything. No problems with entropy, no problems with hydrogen. And of course, it would come out at an enormous velocity, which is what quasars do. It's not because it's the light being emitted as the photons fall in, or the mass falls in. It's the light, the photons that are emitted from this very massive object. And as Holton said, and I agree with him, that the mass of such a star can be so huge that it can give a redshift of 2, 3, 4 or something like that without any difficulty and still be relatively close. So this idea that quasars are all in a distant object, all huge distance because of the expanding universe and therefore the early universe and all that sort of thing is just wrong. Over to you.
I really like that idea, Viv, and it seems to me to better fit what one actually observes at the center of galaxies, which is something which appears to be, well, producing the galaxy in many cases, that you have stuff coming out and then you, because of angular momentum, you start getting these spirals and so forth. It's as though matter's being created or being recycled equivalently at the center of galaxies. That's what you seem to observe just by looking at these damn things. So I'm getting more and more convinced by what you're saying here, I have to say. But I've got another stupid question, probably equally stupid or even more stupid than the last one. But nonetheless, coming back to these sizes, I think what you're saying is that the high luminosity of a Robinson hole or a Robinson donut would occur at a half alpha.
Yes.
Whereas the luminosity of a black hole clearly has got to be outside alpha. They must look bigger where the light's coming from, by at least by a factor of 2 or more than 2, one would have thought. And then by looking at the gravitational effects at the redshifts, and I remember now that people have been able to measure the redshifts, individual redshifts of large objects, of large stars in Andromeda. I don't know how much further M87 is away, whether or not one could look at large objects orbiting the center of that and hence get 2 independent things for the mass. One is the size of the donut, the other one is the redshift from stars circulating. I don't know whether that's possible or not. Have to ask the NASA chaps. I don't know if Brian could chase it up. That would be good. So
Sorry,
if I'm right about the factor of 2 anyway, that was just in the background while we're all talking. So
over 60 million or whatever it is light years. When with a very small base here on Earth, and 60 million or whatever the distance is away, trying to, I think it can be done, but I'm not going to attempt it. The other thing, of course, is that I don't know why people haven't worked this out with the source shield radius, but the mass, a Newton's shell theorem is required to prove that an infinite steady state universe would collapse under gravity. Mass increases by r cubed, gravity decreases by r squared. So when r is infinity, gravity is infinity and everything will collapse in on itself. In my model, you apply the same thing and you find out that mass increases by r because r cubed over r. The denominator, the bottom line, increases by proportional to e to the alpha over r. Well, e to the alpha over r will eventually exceed r, and that's why at infinity there is no gravitational attraction. In practical terms, by the time you're about 10 billion light years away, the attraction of 2 objects on each other is about 10 to the minus 50, which quite literally, as far as I'm concerned, is 0. So that means that an infinite steady state universe will not collapse. End of story. Proof, you just got to have a look at the images taken by Hubble Ultra Deep Field, fully formed galaxies, and then James Webb Telescope goes up, sees greater redshift distances, adjusts photons to real color, fully formed galaxies. Now, you look at the excuses cosmologists are giving about how long space and time, space itself is expanding and all sorts of things. And it's just all they're looking at is an infinite steady state universe. And there is no problem with recycling hydrogen, no problems with entropy, which they all say they are. And I would have to say this, that I am surprised that all of these people turn around and say, oh, I won't mention names, but, oh, it's not that we want to make the universe complex. The universe is complex, and that's what we're trying to get a message. It's not complex. It's simple. It's straightforward. All of the complexities that they say they have are what have been invented by misunderstandings of Einstein's in one case, not understanding would be my comment. It's a very, very simple universe. It has to be. Sorry, carry on.
I have just a couple of clarifying questions. I'm a little unclear still. Does it, to get the donut shape that was proposed here, does the mass have to be spinning around the shape to get that, or is it more of a sphere?
Well, no, the mass doesn't have to, the mass in the center doesn't have to spin. However, it almost invariably will, because everything in a galaxy is spinning. If a galaxy doesn't spin or doesn't rotate, it will collapse in on itself. No questions asked. So every time you pull a plug out of water, the water swirls around. So everything that's attracted, because nothing is moving in.
Directly, right. But I guess the question then is that the reason for the torus shape that you're proposing in the paper?
The reason for the torus shape is that those that are coming in, there's nothing where gravity is strongest. There's no barrier or anything, so they will go straight through. And unless they're caught in the massive object, they will then flow back again. And so they've got these things going back and forth, zipping all over the place. They're going to bang into each other and emit photons. And it will be the greatest number of photons will be emitted by electrons. And that's why the temperature they get is round about 10 to the 10th degrees K.
So then it has to be the case that we are oriented relative to this, what is pictured as a black hole end on, like we're looking at it through one particular axis, but you might see it from a different axis. Is that accurate? Did I understand that correctly?
Well, as I mentioned, the reason why they see a donut instead of a diffuse sphere is because the donut, a thick donut has a very large, you just draw a couple of circles and then draw a line down the, somewhere avoiding the middle, and you'll get a large thickness of material being emitted from the sides, and that's all the way around in 2 dimensions, than you will from the top, because the top has no contribution from the bottom. So the thickness of the top would probably be about a quarter, perhaps, of the total thickness from all of the sides. And that's why things coming, you're looking at this at a great distance, and but that's why the temperature appears stronger down the sides of it. You just just draw a couple of circles.
Well, I guess
No, I don't think that's right, because if that was the case, the center of the sun would look brighter than the edges of the sun look. We're not talking about, we're really just looking at the photosphere, and the same must be true here. The thing must be donut shaped, I think, if it looks like a donut in your model. And I think that could come about because one's talking about stuff falling in, but you're going to get a rotational axis, and it's going to tend to, as you say, stuff that is not coming in on that axis and not hitting stuff, it's just going to go straight through.
Alpha over 2 is where the greatest gravitational strength is, and it's all the way round. You then have particles falling in. They'll come from all directions and they'll come in at all angles. Those that are heading towards the middle, there's nothing that will stop them at alpha over 2. They will continue through. If they miss the object in the center, which they almost invariably will, they will then fall back, and then they're then emitting the radiation at around in a big sphere at radius alpha over 2. But the sun is opaque. You can't shine light through it. This material, light will go through it. It's not some huge dense material. It's optically transparent, because so you've got light being emitted everywhere, but down the sides, and that's what we see, down the sides, it will be much stronger than coming from the center, because the center is only getting a small amount compared to that down the sides. I need to draw a sketch. I haven't got it. Just galactic dust or whatever you want to call it. It's going in, it reaches a maximum of 0.5 alpha. It then goes in, and if it doesn't hit the central object, which it usually won't, and it's very, very difficult to hit something that small, it'll just go back out again. And it's the fact that they're going in and out again and going back out again, it'll have the same speed as coming in. So you have this, I'd say it's more like the sun's corona.
Well, the analogy I was going to use is the Earth's atmosphere. If you look at a picture of the Earth, you see the blue atmosphere only around the edges. That's what you're suggesting, correct?
Yeah, you're not getting any signal coming in from the center. That donut emission spectrum is quite transparent to light, whereas the sun, it's just emitting in all directions.
So to be clear, you're proposing a spherically symmetric system. It looks the same no matter which angle you look at it from. Is that correct?
It's going to look the same no matter how you look at it, unless you could get some really close up, you'd start to notice the difference. But your average temperature at 10 to the 10th degrees K happens to be very, very close to the infalling velocity that electrons will, the equivalent of the infalling velocities that reach.
So my follow-up question would be just, let's assume it is spherical or what have you. There's no singularities in this model. Could we not just apply some numerical methods to this and see sort of what actually happens, in a sense?
Not only are there no singularities, but we all know from Newton's shell theorem that the gravity in the center of an object is zero. Well, all this is doing exactly the same thing. I mean, Newton's gravity by itself predicts that the gravity in the center of the sun will be infinite. But mathematically predicts, but his shell theorem, which you need to do, shows that there will be no infinity at the center of the sun. It'll be very, very hot and very high pressure. I certainly wouldn't like to pay it a visit. But again, this model then also shows, or this metric also shows, that there will be no mass. There will be no gravitational field in the center of the massive object. And this, of course, is exceedingly important in the recycling of everything. And I'm saying it comes via quasars because they have all the properties that are required. And you could work out the mass of an object that's required. Just because the axis of the rotating neutron star cracks. Doesn't mean that it immediately loses all its mass. It still has all its mass, and then you've got to be thinking of something with tens of billions or hundreds of millions or tens of millions of solar masses, and you've got a little crack at the top. How long is it going to take for that to exhaust itself? It would just go on essentially forever as far as the life of an astronomer is concerned. And
it sounds to me as though you've got enough for a paper there to say what these quasi-stellar objects are.
I've got enough for several papers, and that's beyond what I've got in the book. But my biggest problem is that, and the reason why this is never published, what's the standard response you get from an editor? Oh, this isn't standard model, so we can't publish it.
We'll publish it, Viv, don't worry.
Could I suggest a name change then? Instead of calling it quantum gravity, call it subquantum gravity, because it's based on the rotating photon model, which we call subquantum mechanics. So it might be a nice way to differentiate.
Good idea.
Yeah, I don't think that'll make a difference because the comment.
You'd be surprised.
No, it wouldn't make a difference to them, their reactions necessarily, but it'll make a difference to not confuse between the two theories, as John mentioned earlier.
Anyway, gentlemen, we've had a very good session here. and we've had already nearly a couple of hours. So I'm wondering if there are any questions that people have been saving that that they'd like to come in with just now, apart from the excellent set that we've had already.
Everybody understood it. Oh, great.
Thanks very much. That was wonderful.
Viv, it's
Okay.
been a tour de force, this thing, in terms of coming up with a whole bunch of things. And I think it's a marvelous conjecture, and I look forward very much to people devising experiments to look at these areas of things. But I think it would certainly be helped by more of the predictions of what one ought to observe for that massive object, because whether you're right or not, that'll already generate quite a lot of science looking at things. And hopefully they'll come up with the maximum is that R is a half alpha. That'll be really cool. That will be so cool. So well, thank you very much indeed for answering the questions so beautifully and filling us in on a bunch of things. I don't want to wind up straight away, because I don't turn into a pumpkin for another 5 or 10 minutes, but so we'll continue a little bit longer, perhaps just to say goodnight to people, or if there's anything else you thought that you should have said that you didn't say, Viv, that's the other thing. I think this is very well. I think it's brilliant. I think it's a marvelous. Even if you're wrong, I think it's brilliant. So it's a marvelous idea and a marvelous attempt.
If anybody wanted to organize a discussion between myself and some avid standard model proponent, or some general relativity whiz bang guy, I'm quite happy to do it. I don't need much advance notice apart from the time. I just don't think anybody wants to discuss it. I think they just would rather push it aside rather than go into an open discussion. The standard model, they say, oh, it's the most successful theory ever forward, and I'm thinking, the list of unknowns they have is vastly larger than anything they've predicted, and most of their predictions are just about the structure of elementary particles that they get from colliding things in particle accelerators. And you think, their lifetimes are so small. I mean, how's something with a lifetime of 10 to the minus 23 seconds, which is like 2 or 3 rotations of a photon, if I have a photon in a proton, how that can affect anything like gravity or even radioactive decay or anything like that is just beyond physical comprehension. It's all just mathematics.
Well,
and
I think you could say what you can say of the standard model is it's the most successful model there has been for absorbing large numbers of people's attention for the longest possible period of time. So the integral time over model thing is certainly won by the standard model. But I don't think the stuff in the standard model is wrong at all, Viv. I think it's just what you're doing. I mean, gravitation isn't in the standard model. So what you're doing is adding to knowledge, not in conflict with it. And I know lots of very good people working in this area, and they're very serious as well, of course, and they're doing a lot of interesting work in looking at the zoo of particles. Anyway, guys, I think we should call it a day. I think 2 hours is enough for anybody to take out of their early morning in Viv's case, evening in my case, and everything in between. So that's been absolutely great, Viv. Thanks very much once again. Well done. It's been a lovely piece of work there, and very interesting to talk to you about it.
all right.
Okay. Unless anyone else has got any burning stuff they'd like to say, or I think we'll start winding up.
Thanks for inviting me.
Great having
me as well.
you guys. A couple of new faces here, and I'll keep you guys in the loop as well when we do some more of these things, if you don't mind.
Thank you.
Okay.
Cheers, Lou. Take care.
That's great.
Garnet, it's great to see you there.
Right, yeah, great to see you.
Everybody, Jerry,
Yeah.
thanks
Bye for
very
now.
much for coming up.
Bye-bye.
Tyler, great to meet you as well. It's great to see you all, and thanks very much, especially to Viv.